Okay, I think we can start. So, hello everyone, and welcome to this webinar about quantum computing. My name is Jami Rönkkö, and I'm from the Science Support Group. I have worked here in CSC for 4 months now as a trainee on the topic of quantum computing. I will be giving 2 webinars on this subject. This first one will be an introduction to the topic, where I'll be explaining what quantum computing is all about, and then give a picture of the current situation of quantum computing. And then the second webinar will be on 24th of May, where I will discuss a more specific way of doing quantum computing called quantum annealing. And you can ask questions during the webinar, and I will be answering them either straight away or then at the end of the webinar. And this speech will also be recorded and can be viewed later from CSC's YouTube channel. Okay, I think that's it. We can start with the slides. So, the ordinary familiar computing operates on a string of bits, where each bit can have a value of either 0 or 1. Physically, this information is stored in transistors that can have either low or high current value. In quantum computing, the role of transistor is given to some quantum mechanical system with 2 discrete states. For example, an isolated electron in its ground state can be identified with a bit value of 0, and the same electron in its excited state would correspond to bit value of 1. This kind of quantum system naturally follows the laws of quantum mechanics, which are very different from classical physics and logic. The most fundamental change caused by the shift to quantum hardware is seen already in a single bit. An ordinary bit is always either 0 or 1. A quantum bit has more options. When properly isolated from its environment, it can exist in combinations of 0 and 1 called superpositions. While the philosophical meaning of superpositions is still under much debate, mathematically they are just vectors whose coefficients have a special probabilistic interpretation. These complex coefficients here are called probability amplitudes, and they tell how much of 0 and how much of 1 there is in this superposition. When the isolation of the superposition is destroyed, for example, when we measure the state of the qubit will take a definite value of either 0 or 1. And this follows a simple probabilistic rule. The probability that the qubit takes a value of 0 is obtained by taking the square of the absolute value of the corresponding probability amplitude. And likewise, the probability that the qubit turns out to have a value of 1 is the square of the absolute value of this other probability amplitude here. So they can be in an equal position where these probability amplitudes are the same, so there's 50-50 of measuring either one of the outcomes, or maybe there's higher chance of getting 0, or maybe it could be almost completely 0, but there is still some chance of getting the 1 when you measure the qubit. And now, using these qubits gives basically 3 new resources that can be used to do more effective computing. Firstly, the superposition property that I already talked about brings new kind of parallelism, a parallelism that doesn't require multiplying the physical system. And the second phenomenon called interference is important because quantum mechanism is a probabilistic theory, and so quantum computing will also have inherent randomness in it. Luckily, the probabilities of different computation outcomes can be manipulated by an interference. Interference basically means that the quantum states can interact with each other like waves do. When waves go on top of each other, they can either create a bigger wave or cancel each other out. The third resource is called an entanglement. And it follows from the fact that the values of the qubits can get tied to each other, and so that you are able to basically read value of multiple qubits or operate on multiple qubits just by affecting one of them, and this will then in turn affect entangled partners. I will now give a short example of all these quantum effects to give a flavor of how quantum computing works. The power of superposition becomes clear when looking at multiple qubits. The following simple example will demonstrate the quantum parallelism that originates from the superposition of qubits. Consider first two normal bits. This pair can have four different values: 0, 0, 1, 0, 0, 1, or 1, 1. Now imagine we are asked a question. Which one of these four states becomes 1, 0 when the second bit is flipped? Ordinary computer would take the pairs one by one, each time flip the second bit and see if it gives the correct answer. With these four states, in the worst case, we would have to do it 3 times to find the correct answer. Now, let's do the same thing with a pair of qubits. The qubits can be set to a superposition that is a combination of all the possible 2-bit pairs. Keep in mind that there is still only 2 physical qubits that somehow exist in this state of all possibilities. Let's try to find out, again, which 2-bit pair becomes 1, 0 when the second bit is flipped. Now, doing the bit flip operation on the second qubit will flip the second bit value of all the states in the superposition. So already after a single operation, the right answer has been reached there in the superposition state. The 1, 1 state has turned into 1, 0. However, this isn't directly useful to us yet. We cannot see the superposition, and measuring the qubits will now just give some random state. We are also lacking the information that which state turned into which when the bit flip was done. In real quantum algorithms, these issues are fixed by the use of interference and entanglement, respectively. Here I wanted to demonstrate that doing a single operation on the qubits effectively counts as multiple operations because of the superposition. This parallelism will get more and more powerful when the number of qubits increase. The superposition of, I was lagging with the slides. Okay, so here you can see we do the measurement, and in this case, if this equal superposition, we would have 25% chance of getting each of the outcomes. Yeah, so this effect will increase as the number of qubits increase, because 2 qubits can be in simultaneous superposition of 4 states, 3 qubits can be in superposition of 8 states, 4 in 16 states, and so on. And if you would have 300 qubits, they could be in a superposition of 10 to the power of 90 simultaneous states that could be operated simultaneously. And this is more than the number of atoms in the universe, which means that because of this quantum parallelism, quantum computing is way powerful than, can handle simultaneously more information than classical computing could ever do. And then, next I will shed some light on the concept of interference by showing the most simple case, a single qubit interfering with itself in a superposition state. Important basic operation in quantum computing is the Hadamard gate, shown here in the box. So it creates a 1-qubit superposition states. The probability amplitudes of the superposition states are both equal, 1 over square root of 2. It is important to notice that when this gate is applied to the qubit in a 1 state, the second part of the superposition will have a minus sign here. So let's see what happens to a qubit with a value of 0 when the Hadamard gate is applied. We get an equal superposition of 0 and 1. So now if we would measure this state, we would have 50-50 chance of getting either outcome. Then let's apply the Hadamard gate again. It now affects both of these states in the superposition, so it effectively multiplies the number of states in the superposition. Now, first, it would seem that there is still a 50-50 chance of getting either outcome if we now measure the state, because there is 2 zeros and 2 1 states there. This is where the interference steps in. It simply says that we have to add up the similar states. So we add up the zeros and ones. And as we do that, we see that the 1 states cancel out because the other one here has negative probability amplitude. And the 0 states add up to have 0 unity probability amplitude. So now measuring the qubit would, with 100% accuracy, lead us to get the answer of 0. So in hindsight, what we did here on the second line, when we applied the Hadamard gate, we suppressed the probability of measuring 1. This allows us to have a control over the measurement outcomes of quantum computing, and it's a really important part of the real quantum algorithms. Finally, let's look at the quantum entanglement. Another elementary operation in quantum mechanics is the controlled NOT gate that's shown there in the box on the left. So what it does is that if the first, it operates on 2-bit pairs, and if the first bit is 0, it does nothing. And if the first bit is 1, then it flips the value of the second bit. Okay, now let's look at the situation of having 2 qubits, both in the 0 state. Let's first apply Hadamard gate on the first qubit. So we get superposition state like this. And then to this superposition, we'll apply the controlled NOT gate, which does nothing to the first part because the first value here is 0. But then the second one, it says that the first qubit is 1, so it flips the second qubit also. We have a different superposition now. And then let's read the first qubit. There is 50-50 chance of getting either 0 or 1. Now, what about the second qubit? Now it turns out that because of the entanglement property, we don't even need to read out its value to know that it has to be the same as the first qubit. Because in the superposition state will collapse into one of these possibilities. And if the first one is 0, we know for sure that the second one has to be 0 also. And this is really powerful effect because especially if we have more qubits, it's enough that we operate with one of them, and then the other ones will get affected accordingly because of this connection they have with each other. So people have invented some algorithms that use the quantum parallelism, entanglement, and interference, and have been proven in theory to solve problems that are impossible for classical algorithms. So algorithms work by repeating some calculation until they reach the answer. In some problems, the time it takes to perform enough steps to get the answer can be thousands or millions of years. So they are in practice impossible to solve with classical algorithms. Some such problems can be solved in much fewer steps by some smart quantum algorithm. Important, currently insolvable problems that quantum algorithms can solve are search of huge databases, factoring large numbers, solving complicated optimization problems, and simulation of complicated systems such as molecules. Quantum supremacy is said to have been reached when such a problem is solved by a quantum algorithm. The non-academic interest in quantum computing had a big increase in 1994 when a mathematician called Peter Shor published a quantum algorithm that could quickly factorize large numbers. And this is because the commonly used RSA, public key cryptography, relies on the fact that finding the prime factors of large numbers is really hard to do with classical computers. But because quantum computers could do this effectively, it means that if one is able to execute the quantum Shor's algorithm on a quantum computer, one would be able to crack the RSA and access all kinds of encrypted messages and transactions. Now, as you can imagine, using something like the state of an electron to encode information is easier said than done. Indeed, the actual physical qubits are extremely sensitive to any outside disturbances that can give them a kick of energy. Air molecules, thermal energy, physical vibrations, and electromagnetic fields can all alter their value. As a result, the qubits have to be kept in a vacuum near absolute 0 degrees and be protected from electromagnetic fields. And even if the qubits are completely shielded from outside noise, the intrinsic quantum fluctuations can still cause erroneous bit flips. Furthermore, the outside disturbances don't only cause errors, but they will completely destroy the superposition state within a millisecond. This means that any calculations on the quantum computer have to be done before that. Because the qubits that are manufactured these days are still subject to lots of error, they are not by themselves reliable enough to be used in quantum algorithms as ideal so-called logical qubits. Instead, to reduce the probability of errors in the outcome of calculations, many qubits are entangled together to function as a single logical qubit. In this way, if some of the qubits by accident change their value during the calculation, it can be noticed by some smart error correction algorithm and flipped back to match the other entangled qubits. With the current error rates, hundreds or thousands of physical qubits are needed to represent one fault-tolerant logical qubit. Then a few words about the hardware, that is the actual physical qubits. As I said before, in principle, any two-level quantum system can be a qubit. What is required of a good qubits is that they are scalable, have a good connectivity to each other, and they are resistant to outside disturbances, but a bit paradoxically, they need to also be responsive to control signals. At the moment, most promising candidates seem to be superconducting metal loops and quantum dots. In the superconducting loop, a tiny supercurrent can run either clockwise or counterclockwise and will thus induce a magnetic field pointing up or down. The value of this magnetic field can then be considered as the bit value of the qubit. The quantum dots, on the other hand, trap a single electron on a tiny piece of semiconductor and use its two possible spin orientations as the binary information. The current situation in quantum computing is described as being noisy, intermediate-scale quantum era. And all the current machines are at the proof of concept level, with no real advantage over classical supercomputers yet. The development of quantum computers is done both in labs and by commercial companies. Common trend among companies is to give access to their quantum computing system to anyone via internet. This allows people to experiment with early quantum computing systems, and the companies also benefit from crowdsourcing. Here are some of the leading companies in the game with their current qubit numbers. So IBM has 50 qubits, Google 72 qubits, and Rigetti Computing 128 qubits, and D-Wave Systems 2048 qubits. Now it's important to note that the qubit number alone shouldn't be taken as the measure of which system is the best, since the reliability and connectivity of the qubits is equally important. And the D-wave here is actually in a different category than the rest of these computers. Since whereas the others are what is called a gate-based quantum computing, which is basically an analogy of normal computing, the D-wave's computer is a quantum annealer. And I'll be talking much more about it in the next webinar on the 24th of May. But the main difference is that while the other universal quantum computers can be programmed to basically do any algorithm, the D-wave's computer only executes one algorithm. So it's much easier for the D-wave to scale up the number of their qubits. Okay, so the quantum supremacy, this quantum computers solving problems that are impossible for classical computers to solve, might be decades away. But a quantum advantage, that is the fact that quantum algorithm could be faster than classical algorithm in some specific problems, could be reached much sooner. And these kind of problems which could be the first cases to show quantum advantage include simulation of particles and molecules, which would be really useful in drug development and material science, and then optimization problems, such as something related to traffic, finances, and robotics. And then thirdly, improving machine learning, where by using quantum algorithm, much less data would be needed to reach the same confidence levels than what is required with classical algorithms. And it is important to note also that the most effective initial applications will probably be hybrids of classical and quantum computing, since the current quantum computers are still so small that it will be better for some classical algorithm to divide some problems in pieces and then give it to the quantum computer piecewise. And that will be easier for it to solve then. Okay, so yep, it was quite quick. We are already at the main points. So to sum up, the power of quantum computing comes from three quantum mechanical phenomena: superposition, interference, and entanglement. That can be utilized in computing by using some two-level quantum system to encode the binary information. However, fabricating a reliable qubit is really hard because of how sensitive they are to outside influences. Because of this, many extra qubits are needed to do the required error correction. And currently, quantum computers are at the proof of concept level only, where the qubits are too few and too error prone to outperform classical supercomputers. And now my guess would be that quantum advantage could be reached in a few years already, but quantum supremacy only in few decades. Yes, so thank you. That was the first part of this two-part webinar, Introduction to Quantum Computing. And the second one will be on 24th of May on a topic of quantum computing by a quantum annealer. Yes, and now any questions I would like to answer? Okay, so there's a question. When the quantum computing technology is developed, would that mean all the software has to be rewritten? Basically, yes. Yes, because you have to, well, it's like the quantum computing itself, it's basically kind of linear algebra, where it's different from normal computing because, well, it's what is called reversible computing. So you cannot use all the algorithms that you would use in classical computing. You have like a choice of special gates that you can only use in the quantum computing, special operations. But you can mimic any classical gate by those, but you would have to know how to use the quantum gates instead. So what the companies are doing, that they're trying to create this bridge between the way you do the quantum computing and then like ordinary computing, so that you would just call these quantum algorithms without needing to know how they exactly work. And of course, the optimal situation would be that you could just do computing like sort of coding as you do, and just call these quantum functions basically. Yeah. Okay, then another question: why would we need less data for machine learning with quantum computing? How would this be solved, and how much less data would be needed? Ultimately, what is the relationship between quantum computing and artificial intelligence? So I don't exactly know why there is less data needed. Yeah, I guess somehow with quantum computing you can do the sampling in somehow more reliable way, but I cannot say how that is, unfortunately. Relationship between quantum computing and artificial intelligence. Well, the fact that you can basically do faster machine learning with quantum computing is the only connection I know or can think of right now. It will basically speed up the learning of artificial intelligence. Of course, probably there's much more, but I cannot tell you that right now. Any more questions which I can try to answer? If not, then yeah, I think we can stop here, and this recording can be viewed from YouTube within a week from the CSC's webinar YouTube webinar channel. Yep, and also please give feedback and suggest new webinar topics at the link that Mikael posted there on the chat. So yeah, thanks everyone. I was Sami Rönkkö and Mikael was doing the technical and practical stuff here also. So thank you very much.